In the last video we looked at the graph of the function f of x equals x squared plus 1 and considered the area between the graph and the x-axis from x equals 0 to x equals 2. We divided this interval up into n rectangles. Now in this picture we just have 4 rectangles. We made the width of each rectangle the same for convenience. We call that width delta x. We estimated the area under the curve by summing the rectangles. Now to get the area of each rectangle we must multiply the width by the height. Now in the last video we got the height of each rectangle by getting the value of the function at the bottom left corner of each rectangle. That actually gives us the height for this configuration of rectangles. But we could have a different configuration. We could pick a point anywhere along the base of, say, this first rectangle here, call it x1 because we're referring to the first rectangle, and get the value of the function at x1. So we just go up to the curve. The height of this rectangle is the value of the function at x1, f of x1. And you can then see that we could construct this rectangle here. We could do something similar for the next rectangle. Its base lies between 0.5 and 1. We could pick any point in that base, call it x2, and get the height of the rectangle by getting f of x2. So we can do that for all the rectangles, and the height of each rectangle is, in general, f of xi, where I refers to the ith rectangle. I runs from 1 up to n. So by summing the area of all those rectangles we have an approximation to the area under the curve. If we take the limit as n tends towards infinity, let the number of rectangles tend towards infinity, then delta x will tend towards 0. And we stated in the last video that this limit, if it exists, is given by the definite integral of f of x dx from 0 to 2. Without doing any integration, we actually calculated this limit in the last video. We saw that it is equal to 4 2/3. Now in this video we are going to see how to calculate this integral, and we are also going to prove that the area between any curve and the x-axis is given by a definite integral. First, let's see how to calculate this thing. Well, what we consider is the indefinite integral of the function. Now the function is x squared plus 1 with respect to x. Now we saw in previous videos that we want a function whose derivative is x squared plus 1. That's what all of this thing means. So the answer is a third x cubed plus x plus some arbitrary constant c. You see, if we differentiate this here, we get x squared plus 1. C can be any number. Okay, let's suppose we put these limits on. How do we now calculate this definite integral? Well, we get the indefinite integral and then we just draw a vertical line to indicate we're integrating from 0 to 2. So what we do is we plug 2 in for x in the result of the indefinite integral. So we're going to get a third times 2 cubed plus 2 plus c. Then we put down a minus sign, and I'll prove why this is true later on. But then we subtract off the indefinite integral with 0 in for x. So we plug the upper limit in for x first of all, whatever that is, it's 2 in this case. We work out what we have, and then we subtract this expression with the lower limit 0 in for x. Now notice that the c's cancel. C's always cancel, so we can actually not bother with the c when we're calculating a definite integral. So calculating this, we get 8/3 plus 2, so that's 2 2/3 plus 2, which is 4 2/3. The answer that we got by using a limiting procedure in the last video. We did no integration in the last video. Let's look more closely at the area under the graph of the function f of x equals x squared plus 1. We are going to define this new function called capital A of x. It is the area between the graph of f of x and the x-axis from x equals little a to some general value x. So the idea is that little a is fixed, but x is free to move. So in red here we have a of x. So here x is 3.7881, and obviously as we move x around, the function a of x changes. So for example, if we let x equal 4, the area is 40.7785. Let's suppose that we change x by a small amount delta x. Now in this picture delta x is 0.6718, and consider the corresponding change in a when that happens. So when we change x, we obviously change the area by some fairly small amount. We can vary delta x by moving this point here closer and closer to x. We can bring delta x close to 0, as close as we want to 0. We are going to be interested in the ratio delta A is to delta X, delta A over delta X. Now that ratio will depend on X, and it will also obviously depend on delta X. Let's make X equal to 3. We can make X equal to anything we like, but just for convenience I'll make X equal to 3. So in this case delta A is 9.9081. And we divide that by delta x, that's the distance between 3 and this point. Delta x is 0.7881. We could also write delta A like this here. We could get the area up as far as x plus delta x, well x is 3, up as far as 3 plus delta x, that is the area from this point little a up as far as this point here, and subtract off the area from little a up to 3, subtract off that red area. So we take the total area from point A all the way up to point x plus delta x and subtract off this red area. Subtract off A at 3. So that's another way that we could write delta A. And this should be familiar to you. This looks like the derivative of a function. Well, actually this is an approximation to the derivative of A of x with respect to x. And of course something should happen if we let delta x go to 0. We might expect this thing to approach a limit. So let's see what happens as delta x gets smaller and smaller. So we just move this point here towards this point. I'll keep this point fixed at 3. Well, delta x is getting smaller and smaller, as you can see. Delta x is approaching 0. It's now 0.2681. And obviously delta A is getting smaller and smaller as well. So we're going to make delta x approach 0 but not equal to 0. Notice what's happening to the ratio delta A over delta x. This is actually approaching a value. That value is actually 10. I've just went through it there. We don't want delta x to reach 0. So notice that the value that we're approaching, which is actually 10, is the same as the y value of the point 3, 10. And that's true in general. Let's suppose we make x equal to 2.4463. Now, this time delta A is 11.0375, but anyway, whatever, if we make delta x approach 0, you can see that delta A over delta x is actually approaching the y value of x, which is 6.9843. 6.9934. Well, we just passed through it there. It turns out anyway that this number will approach the y value of the point on the graph. Delta A divided by delta x will approach the y value of this point, which in this case is 6.9843. Now intuitively that kind of makes sense, because when delta x is made close to 0, then this blue area here is approaching a rectangle, and the area of a rectangle is base multiplied by height. So the base is the distance between these points, which is delta x, and we could approximate the height by the length of this line here, which is none other than f of x. So, you know, as we get closer and closer, then make delta x go to 0, keeping x fixed, then this blue region is approaching a rectangle with base equal to delta x and height equal to f of x. So in other words, if we take a limit as delta x goes to 0, that means that delta x approaches 0 but never reaches 0. Then delta a over delta x is approaching f of x. So let's see that for x equals 3 again. So we take the limit as delta x goes to 0, and as you can see, delta a divided by delta x is approaching f of 3, and f of 3 is 10. What we said about delta a for the function that we saw in the simulation is true in general for any function of x, f of x, at least for the functions we deal with in this course. So I'm using the graph of the function in the simulation, but we can pretend it's any function. We saw that delta a, the area of this region here, can be approximated by the area of a rectangle whose base is delta x and whose height is the value of the function at x. Now later on we will set x equal to a particular value b, but for now assume that x is a general value, so this point was free to vary as we saw in the simulation. So delta a is approximately height f of x multiplied by base delta x. Of course there's a fair bit of discrepancy here, but this discrepancy goes to 0 as delta x goes to 0, as this point moves towards this fixed point here. We can divide both sides of this relation by delta x, and as we saw in the simulation, delta a over delta x is approximately equal to f of x. As a matter of fact, delta a over delta x can be made as close as we like to f of x by taking delta x sufficiently close to 0 but not equal to 0. So that means that in general we can say the limit as delta x tends towards 0 of delta a divided by delta x is f of x for any function of x, f of x. So we've seen all this in the simulation for the particular function of x. Now of course we know that this thing here, this limit here, is nothing other than the definition of the derivative of a with respect to x. So a, remember, is some function of x. We are assuming that this limit exists, and it will exist for all the functions that we deal with in the course. So its limit is written dA dx, and this will be worked out at x. You could say at x equals x if you like. Later on we look at it at x equals b, a particular value for x. But in general, dA dx equals f of x, the equation of the curve. Our job is to find out what a of x is, the area under the curve. So we are looking for a function of x, a, such that its derivative is f of x. So that tells us that a of x is equal to some function, let's call it f of x, big F of x, whose derivative is little f of x. But of course we have an arbitrary constant. So big F of x is an antiderivative of little f of x. In other words, the derivative of big F of x with respect to x is little f of x. If we differentiate the constant, we get 0. So if we differentiate both sides of this equation, we get dA dx equals d big F dx plus dc dx. Well, dc dx will give us 0. And we've defined big F of x as the function whose derivative is little f of x. We saw in previous videos that we could also write big F of x as the integral of little f of x with respect to x. This was the indefinite integral. And of course we get an arbitrary constant, although I've written it here. Now let's get to our problem. The area between x equals little a and x equals little b. Well, the function a of x is defined to be the area between under the curve between the fixed point a and some general point x. So what does that tell us about a of little a? Well, this is the area between the curve and the x-axis between the fixed point a and the fixed point, well, the point x equals a. Well, that's obviously 0. So we just have this line here. this line is actually the region under the curve between A and A. So again, this red region stretches from little a up to some value x, but if that value x happens to be little a, then the red region stretches from a to, well, just itself. So the area under the curve is 0. We just have this line, the area of a line is 0. Now if we set x equal to b, then this red region is called a of b. The area is stretching from the point A up to the point B, so we're setting x equal to b. So really we just have to calculate a of b, but we can write this, well, we can write our area as a of b minus a of a. After all, a of a is just 0, so we're just taking 0 from this. This is what we're after. If we subtract 0 from it, we don't change it. But if we write it like this, then we can link the area to the integral of little f of x. So what do we do? Well, big A of x is defined to be big f of x plus c, where big f of x is the integral of little f of x. In other words, if we differentiate big F, we get little f. So we plug b in for x and we get f of b plus c. Then we have a minus sign. Then we have to get a of a, which we know to be 0. Anyway, we plug little a in for x and we get big f of a plus c. And we see that the constant cancels out. So we get big f of b minus big f of a. Let's take the example that we've already seen actually, and I showed you how to calculate it at the start of the video, but now we'll tie it in with this. This is the example that we used in the simulation, and the limits run from 0 to 2. So we need to calculate big f of x for this function, so we need to integrate x squared plus 1 with respect to x, get this indefinite integral. So there's a third x cubed plus x plus c, as we've seen already. Now we want to calculate f of b minus f of a, where b is 2 and a is 0. So we plug 2 in for x, and then we subtract off big F of 0. So we write this out with 0 in for x. And as we've seen before, the c's cancel out. So we get the answer that we saw before, 4 2/3. The notation that we use for this is the integral of little f of x with respect to x. We put a here and b here. So in general, when we perform a definite integration, we just get the indefinite integral, but we don't bother with the c, and we apply our limits. So we get a definite answer to our problem. Since the c's cancel, we don't have to write in the c.